we're going to prove the theorem x is a limit point of a if and only if x is equal to the limit of a for some a sub n contained in a with where x cannot appear in the sequence. So there has to be a sequence of a that has a limit x, but x can't be anywhere in the sequence. And so, again, I'll leave the textbook for the formal language, but the idea of the proof is to think about what it means to be a limit point. So let me draw what happens. Here I have a number line, and here's my point x. Now, what I'm going to do is, x is a limit point. The definition of a limit point is that for any epsilon, for all epsilon, there exists an a belonging to v epsilon of x with a can't be equal to x. That's true, right? That's what it means to be a limit point. So I get to assume that x is a limit point, so I get to use this. If I get to use it, that means I know it's true for all epsilon, so I'm going to just start cleverly choosing epsilon. And the way I do this is I say pick epsilon equal to 1. That's how I'm going to start. To do that, I'm going to look at the interval x minus 1 and x plus 1. Right? It's a limit point, so I know there's some a in here. Maybe it's right here. There's some a in here in this interval that's not equal to x. I'm going to call that a1. This gets us a1 because I know 1 has to be in there. Okay, but I need an entire sequence. So the next thing I'm going to do is I'm going to let epsilon, that's step 1, step 2, pick epsilon equal to 1/2. Okay, let's see what happens when we pick epsilon equal to 1/2. X plus 1/2, x minus 1/2. Okay, well, look, a1's still in there, so maybe I'll call this one equal to a1 is equal to a2. So then we get a2, which happens to be equal to a1. Okay, but step 3 is going to be that epsilon equals 1/3. Oh, but now I'm going to go, oh, now I need, now a1 isn't in there anymore. But for all epsilon, there exists an a within the interval such that it's not in there. So that it's in the set a, but it's not equal to x. Right, I really need, I should have intersect a there. So what does that mean? It means that I have to have a new a right there, which I could call a3. Right, step 4 is going to be, I haven't used red yet. Step 4 means you use epsilon equal to 1/4, and you get an a4, etc., etc., etc. So this gives, I can do this for every single epsilon, and that's going to give me a sequence equal to, right, an equal to a1, a2, an, where, what do I know? ai is within 1/i of x. In other words, ai is in x minus 1/i, x plus 1/i. That's what I know for every single one of these. So why does it converge? Well, I can prove convergence pretty easily. Let epsilon be bigger than 0. By the Archimedean property, there exists, I'm going to call it a capital N, such that's a natural number, that's supposed to be natural numbers, such that 1/n is less than epsilon. Then, for all n bigger than or equal to capital N, right, a sub n minus x. Oh, what do I know about this? A sub n minus x, it always has to be in the interval a, that should be, you know, this interval, 1/n, 1/n. So I know that that's less than or equal to 1/n, which is less than or equal to 1/capital N because of this inequality, which, oh, but that's less than epsilon. We're done. So this converges, and we have proved the first direction.